Hi, everybody. And we're waiting for just one member who's coming in. Okay, he's here.
Good evening, everyone.
Good evening, everyone. How are you doing?
Hello.
Hi. Okay, so thank you, everybody, for being here. Okay, I had an echo. Thank you for being here tonight. Welcome to this edition of our live talks. Tonight, we are very honored. We have a very special guest with us. He's going to be speaking about satellites and the SatNOGS project. So it's a very, very interesting topic that we'll be seeing today. Freddy Damkalis has an engineering degree in electrical and computer engineering at the National Technical University of Athens. He's been an enthusiast of open source projects, and he has participated and contributed in several open source projects and communities. For the last decade, I believe, or so, he's been developing in SatNOGS projects, which will be tonight's topic. And also he'll be speaking about the Libre Space Foundation, which is also very interesting. So without further ado, I will leave the floor to Freddy. Hi, Freddy.
Hello, thank you for the invitation. Just let me share my screen. Okay. And let me start the slideshow. Let me know if you see the presentation.
Yes, we can see it.
Oh, cool. So, I'm Alfredos Damkalis, or known as Freddy, and I will present you the key aspects of SatNOGS project. So, SatNOGS project started with a challenge. The challenge was introduced in an event that is organized every year. It's called NASA Space Apps Challenge, which is an event that NASA and other organizations publish some challenges and ask from people during the event, during a weekend, to give some solutions. So the challenge we choose to work with was that a group of CubeSats, satellite CubeSats, was deployed from a launch vehicle or a space station, and we had to find a way to receive them, all of them, and store and present and visualize their data, and also try to connect the NORAD ID and TLSH with the satellite. So what is NORAD ID? NORAD ID is an ID that USA Army gives to the objects that they track with the radars. And the TLSH is for each of these objects, there are some orbital data that are expressed with two lines that is text and numbers that define the orbital parameters for the satellites, for these objects, which most of them are satellites, but we don't know from the radar, we don't know which satellites is which object. So the challenge is also to identify which satellite is which object. Before we start, let's see some basic things about the orbits. So we have three orbits. It's the low Earth one, the medium Earth orbit, and the high Earth orbit. And between the medium Earth orbit and high Earth orbit, we have the geosynchronous Earth orbit, which is the spot where the satellites move with the rotation, with the same speed, the same rotation of the Earth. So you can see here that the low Earth orbit with blue. Let me. I don't know if my mouse can be is visible. Anyway, so we have with the blue the low Earth orbit, then the middle Earth, the medium Earth orbit with the green, and with the red is the high Earth orbit. And to have a better aspect, below here is the distance between the Earth, the zones, and the Moon. So on these orbits, we have several satellites, but in some orbits more than others. So in the majority of the satellites are in the low Earth orbit and the geosynchronous Earth orbit. So in the first two pictures, you can see in from the Earth from a polar view and the equatorial view, and how the geosynchronous Earth orbit satellites are gathered in this perimeter and in this line here in the equatorial view. And if we zoom in in the near the Earth, we can see how many satellites are in the low Earth orbit. Actually, in the low Earth orbit are the most known satellites, like the weather ones, the NOAA satellites, the meteor satellites. There is also the Hubble, the telescope, and also the International Space Station.
So one question, Freddy. In the photograph, each white dot is a satellite?
It's an object, yes.
Okay. Wow.
It's an object track.
Okay.
Yeah, it's actually it's not that size, but you get the the point of how many satellites are there. So other example of LEO Earth orbit satellites are the Starlink ones from SpaceX. So what a LEO Earth orbit satellite means? Here we have the ground track of ISS and how it goes around the world. So when we are in the the low Earth orbit, the satellite isn't always visible from everywhere. It has a specific visibility, and it passes. It does around 15 orbits per day, which means almost one every 1.5 hours. From a specific location, you can see the satellite in a high elevation pass 2 or 3 times per day. When I say high elevation pass, I mean something over 30 degrees over the horizon. And usually these passes last around 8 to 12 minutes from 0 degrees to 0 degrees. And as you can see, it's difficult if you have a satellite to track it. So let's go back to the challenge we had. So we at Hackerspace in Athens, we gathered, and during the weekend we decided to find a solution for this challenge, and we created the SatNOGS project. The SatNOGS project is a global network of satellite ground stations. It's focused to automate how we track and how we communicate with the satellites. Unfortunately, we didn't get any prize or award in this in the NASA Space Challenge event. But the project was so interesting and so fascinating for us that we decided to continue and add more time on it. And some months after that, there was another competition, the Hackaday Prize, which was organized by the Hackaday.io, which is a blog about do-it-yourself DIY projects. And yeah, the theme of this competition was connected devices and, of course, open source. And you see here the subtitle is "You build the future, you go to space," and they say that because the prize was actually a trip to space for one person, or the equivalent amount of money. So we participate on it, and we managed to get the first prize. So the next step was who is going from the group to space, and yeah, that was difficult to decide, and we didn't want uh, to leave it to luck or something like that. So we decided that instead of someone going to space to get the money, and try to make space accessible for everyone. And this is how Libre Space Foundation started. So Libre Space Foundation is a non-profit foundation founded in 2015 here in Greece. The headquarters are in Athens, Greece. It's in the same place with Hackerspace. And we currently operate in 4 countries. As Libre Space, we build only space technologies, 100% of space technologies, nothing else. This means like satellites, components for satellites. We also do research for space challenges and problems that there are out there. And we also create technologies for the ground segment, like ground stations, the SatNOGS project, and also we do some rocketry stuff, but not very. We are in the beginning of this. As I said before, we wanted to make the space accessible to everyone. So we couldn't do that if we weren't 100% open source. So whatever we do is open source. That means the software code we write, the hardware, all the designs, the schematics. Also, we document our processes, and we offer them to everyone. The data we gather also, we publish them back open, and this is how Libre Space Foundation works. So let's go to the project, the SatNOGS project, and have an overview of it. As I said, it's an open source global network of satellite ground stations, and we focus to automate the satellite tracking and communication. This is achieved through an open source stack, which is several software and hardware projects, some services we run, and a collection of data. And on all these projects, we have several contributors with different backgrounds and interests. like universities, organizations, space agencies, satellite teams, of course, the radio amateur community, scientists, engineers, researchers, some spaces enthusiasts, and other individuals. So, what SatNOGS project does? What happens in SatNOGS? So, what we do is ground segment operations. So someone can. So we have telemetry, gathering telemetry and perform telecommand and control in various bands, and we try to expand to higher ones. And the gathered telemetry and data we try to visualize it. We also have a collection of observation artifacts like the data of the satellites, waterfalls, audio, and IQ data, um, as well as some optical data from observations. Another side of the project is that we try to determine the orbit of satellites. We generate orbital data, like the TLE I described earlier, and we also perform satellite identification, and also we record some frequency violations that happen from satellites. Another aspect of our project is the educational opportunities that someone who participates can have. So someone can learn some fundamentals about satellites, like how satellite communication happens and how we analyze the orbits and calculate the orbital data. Someone also can build skills on software or hardware, like radio, electronics, and mechanical skills. And also someone can use and learn the open source tools we use for performing and creating and implementing all the above. And I'm saying about the educational opportunities because we are in an era that people and universities doing their and other organizations doing their first steps in space, and these steps are not always easy. We have seen in the past several issues with satellite missions. Like in the ground segment, we have seen missions that don't have at all ground segment. So they deploy a satellite, but no ground segment at all. Or their ground station is broken, or the orbit that satellite follows, it's not visible from, or have very low passes from the location they are in. Also, we have some issues in the space, like satellites that have faint transmissions or transmit at random times. Transmissions that happen only when the satellite is under the sunlight, or transmissions that happen in only the first days and then stop. We have also satellites that don't transmit at all, or their transmission stop unexpectedly. And finally, other issue is that sometimes the orbital data are not very accurate. So in all these problems, more or less we can help the teams with our SatNOGS network. a network, a global network of 245 online stations and 165 testing stations, stations that are near to start participating in the network. You can see that in some areas we don't have many stations, but this was the case for areas that now have several stations. So as we grow, more and more people join the network, and the network gets bigger and also increases its coverage. So let's see how is the workflow in the SatNOGS project. So we start with the ground stations and the SatNOGS network. So operators of the network schedule observations of satellites, and then the ground station asks the network, do I have a scheduled observation for me? And they get these jobs. And when the satellite is above the ground station, perform these observations and gather the artifacts, create the artifacts of the observations. Then these artifacts are sent back to the SatNOGS network, and they are stored there. The artifacts are the waterfalls, the audio of the observation, sometimes IQ data, and also the data that are demodulated or decoded from the satellite. So this the last type of the data, the frames from the satellites, the modulated frames, are moved from the network to SatNOGS DB. SatNOGS DB is the place we store all the information about the satellites, like their orbital data, their transmitters, and in which frequencies they transmit, and we also gather there all the frames from these satellites. We also have observers external from the network that also contribute frames to the SatNOGS DB service. And now we have all this data. In order to understand what this data means, we need to decode them. So we have the SatNOGS decoders project, and with this project we decode the data and bring them in a human readable form. And when we have data, we want to present them. So we have the SatNOGS dashboards, and these dashboards are the way to visualize all the data. In parallel, with the help of the other artifacts of the network and also SDRF toolset, which also perform observations, we can identify, based on this data, we can calculate and identify the satellites to find which object is of the ones that US Army tracks, which objects are which satellites. And with the same logic and the same data, we can also determine the orbit and also create our own orbital data, our own TLE sets. So more or less, this is the workflow that we have in the SatNOGS project. So it's now time for a quick demo. Let me bring. You see the browser now?
Yep, we can see the browser.
Yeah, we can see it.
Cool. So let's start from the SatNOGS site. So here you can see the home page, so some new satellites that are imported in the database. Some satellites that are close to their re-entry, satellites that get the latest data, and the contributors the last 24 hours that sent frames to the database. These can be, as I said before, external observers or observers from the network, station owners from the network. So we here we gather a list of satellites that someone can see here in the old satellites page. And we can filter them, for example, with their name or other parameters. We can also see the transmitters we have in the database. So we see here frequency, the modulation they use, the baud rate, the space of the transmission, and if it's active or not, and information like that. Also here we can see the spectrum, which transmitters, the frequency of transmitters in the spectrum. Here, for example, we see the radio amateur band for UHF. We can see also the VHF one, which is a little smaller. Here also we have another is the commercial and for other uses UHF band. And yeah, people can check here and visualize the transmitters within the database. So let's go to an entry. Specifically, we are going to see the satellite. So in the satellite page, we can see some basic information like the name, some alternative names in the call sign of the satellite, the NORAD ID, a satellite ID we use for our own purposes, the website of the mission, the satellite mission, the country of origin, here is Belarus. If it's still in orbit and operational, when it was launched, a short description, and we have some links that we'll see in minutes. We can see a map for the orbit of the satellite and where is over Australia. And we also have the details for the transmitters of the satellites in the transmitters tab. So we see that it has two transmitters, one in the UHF, the radio band, and one in the headband. We also see if the radio frequency is coordinated. We see also the modulation and baud rate and all the info. Here, anyone can contribute to this information. So we have the button, so you can take the satellite information, and also you can transmit transmitter, or for each transmitter edit information for the transmitter. So now we have some information. Let's go see what we can do in the network side. So let's go here. So in the network, we can see the observations of the satellites. Here with the cyan color are the observations that are going to happen, the future observations that the stations will perform. Let me show you also here we have a list of the their status. We can also
Freddy,
stations. Yes.
I'm not sure if I'm the only one, but sometimes I have a problem with your audio. It's breaking up. I don't know if I'm the only one.
Lots of audio clip.
Let me stop the video. Improve the.
If you could lower a bit the mic input, you can probably control the audio clipping.
Yeah. It's my CPU right now. Probably you can hear me better now.
Yes, a bit better. Yes.
Yeah. Cool. So here we have the observations. We can also filter these observations. So let's filter the future ones and see what's already. So we see different ones. Some are green, which means we have verified that we received the satellite. There are some orange that waiting for someone to check them and see if the satellite was received on them. We have some failed ones. And with the red color, we don't have any here. We have the observations that have checked and we didn't find any signals from the satellite. So let's go in one of them and see how things are. So here we have the details of the observation, like which transmitter was scheduled, which frequency, again, the transmitter modulations, all these gathered from the SatNOGS DB service. When the pass starts and ends, the maximum elevation, when where it how many degrees the satellite rises from the horizon on which it sets. The polar plot that shows the path of the satellite, and details for the orbital data, the TLE, the two line elements, which, as I said before, stores the orbit parameters and allow us to track the satellites. So on the right side, we can see the waterfall that the organization uploaded. And we can clearly see the signals of the satellites, these yellow horizontal lines. We can also have the audio. Let's wait to load. So in the audio, we can see the waveform, and below it, we can see again the signal of the satellites. Again, it's like a waterfall, it's a spectrogram here. In this case, it doesn't make sense to hear the audio, but we have cases that we have voice messages or communication through satellites. So let me show you one example. This is an observation of International Space Station, the ISS, during an iris contact. Iris contact is an event that happens between some schools and astronauts or cosmonauts, and they communicate. The students of the school ask questions to the astronauts, and they reply back. So here it makes sense to have an audio, and here I'm not sure if you're able to hear it. So this is an example that audio is useful. Also, sometimes we use the audio to try different demodulators and decoders, but because the audio is a compressed a compressed representation of the signal, it's not always useful. And finally, we have also the data that we got from the satellite, the demodulated data, which in this case follow a protocol that's called AX25, which is a usual protocol for satellites to follow. And it's also a standard. And we can see here, if we try to do a first decode of the data, we can see the source call sign, which is the same with the call sign we have in the DB entry. So we now know that the satellite is the right one. The signal is from the right satellite, and some other details. And also we have the encoded message of the satellite, which also they transmit a text that is readable here, but most of it's unreadable and needs to be decoded. There are also some metadata for the observations that give us some details about the setup of the station, and that can be helpful for doing some debugging if needed. So those data, as I said before, they are forwarded back to the database. So let's go again back, and we see the data tab here in the satellite page. We see who sent the latest data. If in this diagram, how many of them have been decoded. And you can also export the data. We have the orbital data here, the information about the orbital data. So a TLE set looks like that. All these are parameters for the orbit. And also the source when we're updated and stuff like that. So how we decode data? We talked about the SatNOGS decoder. So the SatNOGS decoder is a collection of actually not the decoders, but the description of the encoding structure and the decoding structure. So we use a project that called KaiTai. And you can find it in the kaitai.io project. And here we just describe like that, describe how the frame is structured. And this project allows us from this description to create in several programming languages the actual decoder. So for the Qubel, we have this KSY file that describes how the frame of Qubel satellite is structured. And using this, we can produce the decoder software that will be used to decode the satellite data. And now we can decode all these data. We can move to the dashboard. We can move to the visualization of these data. So here we have a Grafana that helps visualize different data. So here we can see the case. We have 7,000, more than 7,000 frames gathered from the satellite, from all these stations and observers. Actually, the telemetry of the satellite, like battery voltage, battery current, solar panels, and temperatures. For all these stuff
We lost your audio again. Sorry, Freddy, for the interruption, but we lost again your audio.
Can you hear me better now?
Yeah, a bit better, yeah.
Okay. Yeah, again, it's the CPU stuff. Fix that. Anyway, so so we have the dashboards that the satellite teams. Oh, do something else. Let me. So I have this as a backup. Oh, I forgot to show this. Yeah, I will do it after that. So the dashboards look like that. So we have all the details, so visualized from gathered from the frames that satellite sends. All this information decoded and visualized in these dashboards, allowing the satellite teams to know the status of the satellite and plan the further the future operations for the satellite. We have several examples that satellites using all these observation and all this data to and change the way that they were operate their satellites. So what I forgot to show you is how we schedule the observations in the network. So let's schedule for QBEL some observations. So we go to the scheduling page. We choose the satellite, QBEL2. We choose the transmitter we want. Here also we have an indicator how many of the observations were successful with green, how many are not yet processed, so we don't know, and with the red, how many were not successful. So we choose the transmitter and also the stations that will perform, that will participate in these observations. So we set the start and the end time of the period that we want to observe the satellites, and we hit the calculate button. So now the algorithm tries to find all the passes for the selected stations of this satellite. So you can see here we have plenty. Each line is one station, and each box, colorful box, it's one pass. So you can see plenty here. Actually, there are 506 observations for one day for this satellite. So we can also filter them, like we want only those over 50 degrees elevations. So we filter them, and then we can hit the schedule button and schedule these observations for QBEL. And this is how it's done right now, how we schedule. So the next step is the client come and communicate with the network, ask for the jobs and perform them, and then send the data we send. So let's go back to, oh, I forgot to show this also. Some of the data are decoded into images of the network. Here is the NOAA 15, which sends these nice images. So here is over Europe. And there are also other missions that also transmit images. So let's go back to the presentation. Give me one moment. So we've seen the dashboards, and unfortunately I cannot demo it right now. So we are going to see some screenshots here. It's how we identify the satellites. On the left side, we have the SDRF tools, and at the right side, it's one of the waterfalls from the network processed by a software we called IGNOS. So what we see here, the way we identify the satellites is by using the Doppler effect. So when the satellite passes over our stations and transmits signals, due to the big velocity that it has, it creates the Doppler effect. So we receive its signal in a different frequency than the satellite transmitted to. So by knowing the orbit of the satellite, we can fix that. So in the network, we fix that during the observations. So we expect the signals to be on the center of the frequency. So they should be in a straight line. Here it's a little curved, which probably means that the orbit data we had weren't very accurate. Or we followed wrong orbital data. We used wrong orbital data. On the left side, on the SDRF tools, you can see the frequencies on the y-axis, and you can see that the signals follow a curve. So now we have the signal corrected or Doppler corrected or not, and we have some orbital data for an object. So what we do is to draw the expected line, the expected curve for this object, and if this goes over the signal we observe for the satellite, then we can identify the satellite. So here you can see the green line, which is the orbit we expected from the object 47314 with this NORAD ID, and we can see that follows the transmitted lines here, the vertical yellow lines. In a similar way, here we have the signal, and with the red line, which is the expected orbit, we can see that it follows almost exactly the satellite. So here we can safely say that this satellite is the object 47314. Now we have this data, we can also perform, we can also determine the orbit and generate a new orbit. Here, with the red dots, we use the SDRF tools and the data from our observations. And here, with the red dots, you can see the observed signals of the satellites. And with the gray and red line is the orbit of the satellites. So with this tool, which is called RFFT, we can tweak and change the parameters of the orbit and find the best fit on our observational data. And when we have this best fit, we can produce the TLE set, the orbital data, and we can publish it and use it for the next observations. So here are some statistics about the SatNOGS project. On the network, we have more than 400 ground stations. we perform more than 9,000 observations per day, and we gather around 70,000 demodulated frames per day for several satellites. We also have performed until now more than 9.6 million observations in the last decade that SatNOGS project, SatNOGS network works. In the SatNOGS DB, we have thousands of satellites and transmitters, and we also have gathered more than almost 240 million demodulated frames. Some other stats, we have created more than 100 decoders. We have 150 dashboards. We have generated more than 600 TLE sets. And also we have performed 200 satellites identifications. And with this, let's see how can someone contribute in this project. So one way is to just build a single station. All that it needs is a Raspberry Pi, and a software-defined radio device, an SDRA device, and just an omnidirectional antenna. And with this setup, you can start and then build on it. Alternatively, you can, not right now, in some months, you can find the SatNOGS kit, which is a similar simple setup to start and to build the stations. So it will contain all the components needed to get you started. Another way to contribute to the project is the development, either of software or hardware, for adding new features, fix some bugs and open issues that there are, write some tests, or document the code or some processes we follow. Also, you can participate in the operations of the network, of the project in general. So you can help us gather information about the satellites and their transmitters, and help us gathering all of them in the SatNOGS DB. You can also help us to create decoders. We have several satellites that we know how to. We have documentation how to decode the frames we have, but we haven't built a decoder yet. Someone also can build dashboards, so get the decoded data and visualize them. Also help on scheduling observations, especially on some special events, and also help us with orbital analysis and identify with us satellites. So there are also other ways to contribute. I mean, the SatNOGS project currently is a huge project, and with many areas that someone can contribute to it, and I am sure that everyone can find something interesting in the whole project to contribute. So I invite you to join the project. So we have the websites, the satnogs.org and Libre Space. Once we have a wiki, I'll show you. Let me show it to you right now. So this is the wiki, which have some information on how to build a station, how to get started, how to operate. It's not a complete guide. We try to update it as often as possible and keep it up to date. But you can help us also on this area. And we have also the community forum. Oh, let me show you this too. So here is the community forum where we discuss things about operations, satellite launches. We also support people that build stations or helping satellite teams that ask questions and all this stuff. And we have also the repositories where all the code and the designs and the schematics, everything that we create for the project is in there for anyone to see and contribute. And yeah, you can also contact me through my email, or you can join. Oh, I forgot to add it here. It's in the wiki. Actually, you can go to contact and get in touch. And here we have some details how we can join our chat rooms in the Matrix service. We have some rooms where we communicate more directly, especially, and we are especially active when new launches happen, and we try to hunt and track the satellites and coordinate. And with this, I'll thank you for letting me present SatNOGS project, and I'm ready for any questions.
Oh, thank you very much, Freddy, for this presentation and for the useful information. Before we open the floor for questions, let me see if I can share my screen for 1 second just to show. I don't know if you can see. Can you see my
Yes.
my screen?
Mm-hmm.
We have already thanks to David, we have 2 stations right now participating in the network. HI0 SDR1 and HI0 SDR2. They are actually in the network, I believe, working perfectly. So I will ask David now, so if he has any comment before opening for questions. Sure, go ahead.
Just let me just to comment on this. That first, thank you for starting with the ground station and expand the network. Usually, one questions I'm getting is, okay, now you have in your area 2 stations. Is there any meaning to create more stations? And the answer is yes, for several reasons. One reason is that sometimes some stations go offline or have issues, so to have another station in the area help us to not lose the coverage of that area. Another aspect and use of having many ground stations in one area is that we can track many satellites at the same time, and especially when the satellites are deployed, they are until they are separated, they are in a group. So having more than one station means that we can track more than one of these satellites and offer to the satellite teams data and observations of their satellites. So yeah, that was it.
Thank you for that. David, go ahead.
Okay, I would like to thank Freddy and the rest of the crew for giving out a hand in setting up the 2 stations. We are still currently testing the antennas being used and try to improve a little bit more the reception. But that's what I wanted to express for all the help I got from you guys when I started doing the project, and also for accepting the invitation in doing this Zoom with us. I would like to pass the word to Oscar. He's one of our members, and he actually built a satellite, and he has a couple of questions for you.
Thank you very much, David. And thanks to you, Freddy, a lot. Actually, I'm pretty amazed by the project and everything. I've been kind of looking through it for a few days now, and I have a few questions. First of all, regarding the program that you guys use, the computer program for the satellites, I saw on the wiki that it was made for the Raspberry Pi. Is there any way to run it on, for example, an old computer, an old laptop that we could have laying around? Or is it only like available to run it on a Raspberry Pi?
Yes. The Raspberry Pi is the easy platform to to set it up. But yes, you can. We have several stations that are set up in old laptops or PCs or anything. So it's possible. Currently, as we are in some stages, you may need some extra help to build it in a laptop. But this is why we have the community forum and people there that will help you to set it up in the platform you want.
Okay, perfect. Another question that I had was regarding the antennas, the project antennas that you guys have on your page. So from the antennas that you show that you guys can make, for example, the Jaguar or the helical antennas, which one would you recommend to build? Which one's better? Which one has the better efficiency?
Hello, Freddy. I think you are mute.
Yes, you're right. Sorry. So what I was saying is that this it depends on what you want to do. Usually, the best setups are with directional antennas, like Yagi or helical ones, and with a rotator that allows to point to the satellite and gather less noise from the, the environment. However, we have seen in some stations very well behaved omnidirectional setups with very good reception. So I guess it's a combination of things, but and also it's how much money you want to 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 spend on this, and how complicated you want your setup be. Is all these parameters that you need to think before setting up a station. But yeah, to be honest, the best station we have right now, it's a very big dish, which is actually a telescope. And from time to time, yeah, we use it in special occasions for helping us when the satellites, for example, they haven't deployed their antennas, but they transmit. So they have very, very faint signal. So we use this huge dish and we managed to receive it. But yeah, this is the exception, of course. But yeah, a setup with a rotator and directional antenna could give a very good performance.
Okay, that answers my question perfectly, and it actually gives me a lot of insight for me because I was thinking about building a station myself, just like David did. But yeah, I'm gonna go to my next question. So I'm a satellite enthusiast myself. I gotta say, as David told you before, I'm into building the CubeSat Sim project from MSAT, and I have it right here. It's still not finished, but yeah, but it's pretty close to finishing. But I have two questions regarding this satellite recognition from SatNOGS. The first one is, what's the minimum requirement for a device to be recognized as a satellite in your platform?
When you mean recognition, what do you mean?
The minimum requirements, for example, which data does it need to send to be recognized as a satellite and to be tracked by the SatNOGS network TV, or let's say, for example, does it need to send in a specific string of data to be recognized by SatNOGS, or is it something else?
Sure, I'm not sure I got you.
I think what he's trying to ask is, what does it take for SatNOGS to track a satellite? How does a satellite qualify for to be tracked?
So how a satellite is integrated in the SatNOGS? Yeah, this is very easy. Someone from the satellite team comes into the SatNOGS, and there is a process first to add the satellite in the database and all the information about it, and then we need also some orbital data to start with, and then we can start observing it. I mean, we don't we track everything that we know how to track it. There isn't any limit or anything. The only let me say this parenthesis. The only limit we have is when a satellite currently is not, it transmits in the radio amateur bands without having a coordination for its frequency. This is a limitation that we decided as a community and as project to add in the network and the SatNOGS project in general, in order to press the satellite teams that use the radio amateur frequencies to coordinate the frequency, because there are many examples that satellites transmit over other satellites, and this can create issues with emissions. So what we do with these, let's say, uncoordinated satellites is that we track them for record their non-coordinated transmissions. We track them also to identify them as objects in order to contribute to the space situational awareness, to know who is who up there. And we observe them only for these reasons, not for gathering data and help the mission. This is a decision and a policy we have in order to ask some pressure to give some pressure to the satellite teams to coordinate their frequencies. So
excellent.
yes, the integration can be done, and you can also what we usually suggest to satellite teams and missions is to come to us as early as possible and try test the satellite. Also, they can. There are teams that have used the dashboards and the some development environments we have for network and database, and they use them to perform tests and development during their development stage. So as early as possible, you can come and start integration of the satellite. And we are there. I know it's currently it's a little complicated as a process, but we are there to help you to go as smooth as possible.
Okay, now I'm going for my last question. This one's gonna be a very direct question. So how can I register my CubeSat SIM in the platform? Because I was checking the Grafana page that you guys have, the network page, I believe it was, and I saw that there was already a CubeSat simulator registered. So I thought to myself, hey, now that I'm making one, I can register it. How can I do that?
Yeah, I think AMSAT has a similar way to visualize data from CubeSat simulator. I'm not very familiar of the stats right now. Maybe if anyone else knows, but yeah, they have tried an experiment with the Grafana dashboards we host. So right now, if you wanted to add the simulator, the satellite simulator, I would suggest to go to the development site of the SatNOGS network and SatNOGS DB. Add there your own satellite, name it whatever you want. Set up a station for the development network, the development instance of the SatNOGS network, and start beaconing with a simulator. Your station will receive data, they will be forwarded to the DB, and there you will need to create a decoder with a kite struct for your simulator CubeSat. And then you can create the dashboard in the Grafana. It's the same as any satellite. This is more or less the process.
Okay, perfect. Thank you. Now I'm gonna pass the microphone to my friend Eduardo Sturla. And go ahead.
Hello, Freddy. Good evening. How are you? Great talk. One question. I saw that you identified satellite because of a Doppler signature, correct?
Yes.
Okay. You need to compare that Doppler signature with some reference. How do you go about recollecting the database for the reference Doppler signature for each of the different satellites?
So the reference we have is actually the TLEs, the orbital data that USA Army publish. So we have the orbital data from them and the object. So we know how the signal, which curve the signal will follow. So if this fits what we observed, either in the SDRA tools or the waterfall we gather from stations, and this and there isn't any other object from the same launch that fits these signals, then we have an identification. So we know that this object is this satellite.
So it's very important that the reference data that you get from either government agency or NOAA or any of the other is precise. If you don't have good reference information, then you're going to encounter odd positives. Okay. One last question. I saw that satellite Libre, the foundation, you've been able to put up one satellite in the air in 2017, correct?
Actually, until now, we had 3 to 5. I'll explain that.
Okay.
So the first one was UPSat,
UP,
which was or UPSat, whatever. This was our first satellite. It was a collaboration with University of Patras, university in a city near Athens, and this was built very quickly with no experience at all. It performed some. It was functional, but had some issues, and this was our first 2-unit CubeSat. The next mission was the cubic one, which these are there were two pocket cubes. This is 5 by 5 by 5 centimeters satellites, and we have two of them. The first two were expected to launch with the first Firefly launch. Firefly is a new launch company, but the rocket failed, so the satellites were destroyed, or not exactly. The satellites managed somehow to survive, but this is another story to tell. So then, after the launch failure, the Firefly contacted us and said, "Do you have two more to send?" So the next year we sent, and they managed to be deployed. Two more pocket cubes, Cubic 3 and Cubic 4. And we are expecting our next missions. So we expect now with the Ariane 6 launch, we have a payload on the rocket. It's called SIDLOC. Actually, it's a device that will transmit certain signals that will help us to make the identification and the orbit determination more easily. This is the mission of this payload. And also with one satellite, we are going to test our communication board, which is called SatNOGS comms, and this is also deployed in the Ariane 6 launch. These are the next month's missions, and we have some more CubeSats that are coming in the next year. We build them. Just to add that on these projects, everyone can participate. I mean, if someone wants to contribute somehow and want to participate on these projects, we are open to contributions.
Okay.
One more detail.
Yeah.
But of course, these projects are also open source, and as a policy that we have is that open source means that it is open from the first day. So you will see the initial description, just the description, and how slowly each project has been built, what changes have happened, and all these things. Yeah, go on.
Okay. If Santiago can let me one other question.
Sure, go ahead.
Yeah, okay. What is the main challenge of putting up these cube satellites? I mean, is it only payload considerations, or are there other particular challenges that you found in your experience?
To be honest, I haven't participated a lot on the satellite building, but from what I've heard and discussed with other contributors is that there are some standards you can follow. There are some test you need to pass. So all of them have their own challenges. I mean, some electronics, the power budget also, it's very significant. How many batteries you have, how much power you will spend, how much power you will gather through the solar panels. All these are challenges that exist, and I want to point out at this point that it's very important to have open source projects that you can check and see what other people have followed and how solved all these challenges. This is something that we didn't have on UPSAT, on our first satellites, and maybe if we had something like that, maybe it was more successful. But for example, the cubics were the cubic missions were more easier to to be implemented because we have the experience, and we had also some satellite teams that open source some parts of their missions and their projects. And yeah, this is what we are trying to do, because the statistics said that around 50 to 60% of the satellites face failures when in orbit. Some of them they never transmit or they never be alive, and some of them stop or have different issues. So for us, it's important to have an open source ecosystem that we can document and have all the lessons learned during development of a satellite.
Thank you, Fred.
You're welcome. You're welcome.
Is Chago still with us? I think is he still on? Santiago. Okay, I see Mexico. Mexico, go ahead. You can ask your question.
Okay, thank you, Freddy, for all this great information. I actually had a question about satellite frequency violations, but you already covered some of that. I wonder, however, what do you do with the violation reports, and do you get any feedback from the institutions that you send that to?
Yeah, actually, we are in close distance with Yaru. I always forgot the abbreviation, what it means. It's International Amateur Radio Union. Yes. So Yaru performs the coordination for the radio amateur frequencies. So it checks if the satellite is indeed the radio amateur mission, which is one aspect, and the second is to find a frequency that they can use and transmit. Okay. So for we currently don't send to anyone these violation, let's say, recordings of frequency, but they are there for anyone to check and use them as they wanted to. Just to mention that we are not let's say track all the kind of violations. We don't have that capacity right now, but we so we are limited right now on the amateur bands and on the coordination level, on the IR coordination level. And it's also kind of complicated. The and yeah, geopolitics also get part on this. So it's difficult to say who violates and who is not, and there are gray areas. So currently, our capacity is on the radio amateur frequencies and bands, and we try with Yaru to put some press on satellite teams to be coordinated and make the best on the bands that we as radio amateurs have available.
Okay, thank you very much.
Well, I have a question. Maybe I can mention the elephant in the room. Do you use any kind of artificial intelligence in the process?
The quick answer is no. The long answer is that there are many aspects of SatNOGS that could use artificial intelligence. For example, for checking, for doing what we call vetting process, which is that we get the observation artifacts and check if the satellite was visible, if was transmit, there are transmissions of the satellite signals. All these could be potentially performed by an AI software, an AI instance. We have another project. It's outside of SatNOGS project, but under LSF, under Libre Space, and it's called Polaris. And what it tries to do is to get the decoded data from the satellites and try with AI to find a correlation between the different measurements, the different sensors, and also it combines some weather, space weather data. So it tries to correlate all these and find interesting findings, like
doing data mining.
Yeah, exactly. And with this, you can probably find and create some alarms for the status of the satellite, or find that I don't know, when this measurement is negative, then maybe something bad is going to happen, or what we can do, stuff like that.
Okay.
So yeah, this is a project that we use AI.
Okay, thank you. I'm not sure if anyone has anyone with a question. Apparently, there's no more questions. So I guess we can free Freddy now.
Ask David, is he have his tracking for SatNOGS?
Freddy, thank you very much for taking this time and making this presentation and this conversation. It was great. It was excellent, useful information. I think we have Waskar here, which is who's very enthusiastic about it. And I know it's almost 4 a.m. your time.
Almost 5.
Almost 5. So we're gonna leave you to have breakfast, maybe. And on behalf of SDRA, we thank you very much for your time and the presentation. Certainly, we're gonna be collaborating with you constantly in the future. So before David sleeps, David, go ahead to close this.
Thank you also for dedicating the time to us, and certainly we will keep on collaborating and adding more stations to the network and participating in the community. Thank you again.
Thank you for the invitation, and see you around.
Thank you.
Bye-bye.
Thank you very much, Freddy. Thank you, everybody.
Bye-bye. Good night.
Thank you. Good